Okay, so I'll try to wrap up the group theory now, to the extent that we followed it. So including the this kind of a homework for you to think about. Okay, and so don't forget that this is if you are likely to take a linear algebra class next, that would be the most relevant part of the course. So anybody is taking linear algebra, right? So you're facing the already proofs to begin with, and then you're facing this abstract approach to algebra, right? Except it's a different algebraic structure which is richer with other operations. Not just addition, but also scalar multiplication, right? But other than that, the idea is there. Okay, so let me review of what we have accomplished, the way we proceed here. So review and preview. Well, we started with real numbers, so at least we can think as if we did. So real numbers, and then they have many structures, or maybe not too many. But one of them is the algebra. So algebra we can add, and we ignore multiplication. Okay, but it's certainly not a problem. So we go abstract up with algebra, specifically groups. Okay, and then there are other groups. It is an abstraction not only of the real numbers R, but also of Zn. Okay, so in essence, we took this trip. So from the real numbers, understanding the algebra of real numbers goes way back to elementary school. In this class, we concentrated on the actual algebra rather than no matter with what we do algebra with, but rather what algebra is, so what it means to add numbers, and we distilled it to just 3 or 4 axioms, and those axioms formed the abstract idea of groups. And then only we illustrated that idea of that algebra in the abstract with one more concrete example, Zn. Okay, so that's what we did. And once again, you can illustrate it with Z, all the list of other sets of with algebras, Z, Q, and C, and vector spaces, Rn in particular, also all the examples. But this one is the most prominent example, I think, because, well, certainly it's not covered by linear algebra for one, and secondly, the algebra is actually very different from the algebra of real numbers. Well, the algebra is the same. What's different is the set. Reals, integers are all infinite, and this one is finite. But the algebra turns out is exactly the same as far as the basic properties are concerned. Okay, but real numbers have more stuff in them besides algebra. What can you think of? What can you do? What else can you do with real numbers besides algebra?
Are you asking for, like, since you're saying like algebra, are you asking for like different like sections of math that you can use?
Math, yeah. Doing what math have you done with real numbers? What? Like geometry. That's right, geometry. You can do geometry, and it is usually intermixed with algebra, but it doesn't have to be. So that's where we're going. So, well, that's exactly what we're going to do. Okay, so we have been doing so much algebra, now we just take it and throw it out entirely. Okay, so in other words, so we are different structures studied separately in order to actually understand what they are. Those operations, algebraic operations. Now what can we say about geometry in general, not just geometry of real numbers? Okay, so one way to just I want to have one more illustration of what I'm talking about. And that is everything starts in calculus, and that's where everything mixed up. So it is actually a good idea to try to unmix it, even though it feels sometimes like you were trying to unstir cream from your coffee. Okay, but it can be done. So this is what I'm talking about. I'm talking about limits. Okay, so a limit, you can certainly talk about limits of functions, but in continuity as a result. But let's take a simple example, and that is a limit of a sequence. So we have a sequence, say an converging to A. Okay, so we are going a sequence of real numbers. So we're still starting the same place, real numbers. Now we're talking about sequences. We're talking about convergence. And, well, on the surface, there's no algebra, but actually, if we go to the definition, there is. So what does it mean? Anybody remembers the definition of the limit? Or at least the beginning? It starts with definition of limit, of any limit. For any epsilon. Okay, so for any epsilon, there is a delta if you're talking about functions, and here it is simpler, so there is an n. So just like always, the quantifiers in the beginning followed by a statement. So for any epsilon greater than 0, there is an n, such that for all or any, doesn't matter, n larger than n capital, an minus a is less than epsilon. Does it look familiar? It's calculus 3, even though you can, it is simpler than what you see in calculus 1, limits of functions, because where you have epsilon and delta, and this one, I believe, slightly simpler, so you don't have to think about functions, right? So it's nothing but a sequence of real numbers, nothing else, and that's what this limit is. And so just to remind you that 1 over n converges to 0, and all of that stuff that you must remember from calculus 2. Okay, so if we look carefully now, what do we see here? We actually see 3 things. We see the 2 things that I already mentioned, and there is a third one. So starting with algebra, do you see algebra in the definition? The algebra of real numbers. These are all real numbers. Epsilon n might be an integer, and lowercase an integer, n, a are real numbers. So where's algebra? It's not a trick question. What?
What do you mean, where is it?
Well, there are 2 lines of text. There is somewhere algebra there being done.
The a n minus a?
That's right. Yeah, I wasn't, like I said, it wasn't meant to be a trick question. So algebra is there, but it is the absolute value that is geometry. Okay, so if you like this one, this part is geometry. Because what is the absolute value, geometrically speaking? Absolute value of x is what? It is the distance from x to 0. The distance in that literal sense that we know, not in the algebraic sense that frequently you see in calculus, where you speak of a distance while you mean more like displacement. So the coordinate, in fact, if you to the left of coordinate of x is a number, okay? Its coordinate on the line is also x. X indicates the distance to the origin, but it is positive when to the right, to larger than 0, and it is negative when it is less than 0. So that's not exactly the distance we're talking about. This is a distance that's there why we have absolute value. It has got to be larger than or equal to 0. So that is the distance in the geometric sense, not in the algebraic sense. Okay, so, but then here they mixed up together, and as a matter of fact, the absolute value of x is the distance from x to 0. In the meantime, absolute value an minus a is what? The absolute value of the difference of two numbers, what is it? The distance between them, right? Between these two, an and a. Okay. Before we pursue this, let me point out the third structure that is visible in the definition. So this definition, there is the third structure that is neither algebra nor geometry. Can you point it out? So let's say we have studied algebra in the abstract, so we know it is about addition, subtraction, and so on. Okay. So now we're starting on the down the road of geometry. So it will be about distances, just almost entirely. So what else is there in these two lines of definition? That is neither algebra nor geometry. Also, so I already covered. I put those symbols, those lines to indicate algebra and geometry. So just look outside. What else do you see? See these signs? These are the signs. This is neither algebra nor geometry. It is especially noticeable in algebra. Think about, we were talking about Zn. Is there an order of, can you say that 1 is less than 2 in Zn? It is cyclical. Okay, so there is no relation of less or larger. Less or bigger, smaller. There is no relation in Zn. In R, yes. In Z2 also. In Q, but not in Zn, nor in any vector space either. So there is no relation less, more or less. So the algebra is certainly is not, that relation is not covered by algebra. And you can also, so it's called order. So maybe if we have time, we'll look into that. And it's also doesn't fall under the geometry umbrella because it will be entirely about distances. So distance. Okay, so as you can see, three things that come up very, very different, that come up in the same definition, one of the most elementary definitions of calculus, and you have entirely about real numbers, and there are three structures of real numbers that are present simultaneously. So we split them up. So we already did that with algebra, and so algebra that was entirely devoid of any geometry. That's what we looked at up until now, and then it also order also did not come up. It was not a part of analysis. So less or larger, it is not algebra. Okay, so it is an order relation. And order relations have separate interest. If you want to generalize an order relation, an example would be, so we will have some more examples of geometry here, but you can certainly think of examples of order, say, as an example of, concrete example of an abstract order idea is like family relations. Family relations, so older. Well, one person is not older, rather, but being a descendant of the other, that creates an order relation between them. Well, anyway, we'll look into that if we have time. But right now, let's look at the geometry, and we already see that that we already can recognize, or at least let's try to recognize that we already need no algebra. So even though the algebra is explicitly right there, an minus 8 is algebra, but right here, I was able to explain the same idea without using any algebra. I know what I care about is the distance between an and a. That's all. Okay, so where is algebra? It is a distance. So well, let me try to explain this one more time. So if we're talking about the real line, so these are my x's, r, okay? So the difference between algebra is, for one, is, so if it is algebra, then we have all these markings, 0, 1, 2, 3, and then we do algebra with them. So 2 plus 3 over here gives me 5 somewhere else. So that's roughly what the algebra looks like. And in the meantime, we don't really need that if we're talking about geometry. All we need to do and be able to is, if we have two numbers, say 1 and 3, I measure the distance, and the distance is 2. How I measure distance doesn't matter. I do not really have to do subtraction in order to do it. So why is it important? Once again, elsewhere, you may have seen this already. Elsewhere, that algebra that we saw might not be as applicable anymore, such as straightforward subtraction, and the absolute value of the subtraction won't work once you go to, say, plane. So what if a sequence is not a sequence of real numbers, but a sequence of points on the plane? So I'm looking at what I've got here. So this is my definition. Okay. And what can happen is very simple generalization that you saw in calculus 3 is a sequence not of numbers anymore, but rather a sequence of points on the plane. So what are real numbers if not points on the line, which is I just illustrated here at the bottom. Real numbers are points on the line, and that works out fine. And we can utilize algebra easily. But if they are on the plane, it is not as obvious anymore. But the idea of convergence still matters. So you can think about this some kind of spiral, and it is spiraling on a point right here. Okay, so that point is A, and this is the sequence AN. And so you can still ask the question: does this sequence converge to A? And it is the idea of convergent sequences related to what in calculus? In calculus 3. So this is my plane, and I have a convergence of points. Convergence of sequences is related just to continuity. So if you want to speak of continuity of, say, a parametric curve, you have to examine the convergence of sequences, and as well as in if you're talking about continuity of functions of two variables, for example. Once again, this plane becomes the domain of that function. Once again, you have to speak of convergence of sequences. We're not going to talk about that, but certainly you should refresh your memory about calculus 3, how that works out. Okay, but once again, we want to talk about convergence of sequences on the plane or high-dimensional spaces, and that's where the algebra is not as simple anymore. You can still try to do vectors, but we will going to pursue a different idea, and the idea is simply assume that we already have a way to measure distances. It is a plane, it is a piece of paper, so everything is happening on a piece of paper, and all I want to be able to is to measure distances. So this is P, this is Q, and I'm talking about dpq. You may even have seen this notation, dpq, indicating the distance between a point P and Q, either on the plane or high-dimensional space. Have you seen notation like this? Yeah, so in calculus 3, so you certainly there's other ways to do it using vectors, therefore algebra, but really we're pursuing it is in all the way so that dropping algebra out of sight altogether. Okay, and it can be done. I just used that language that I already used. I have that absolute value here that is the distance between 2 points. So these are now points. They are numbers, but they're also points. And then I use that idea over here, and I just replace this whole business over here. This is the only troublesome part, and I replace it with I could use words to begin with. The distance from AN to A is less than epsilon. Okay, so as long as we know how to measure distances on the plane, and we do know, remember there's a distance, so well, let me get to that in a minute. Or I can rewrite using that notation on the right, so DAN A is less than epsilon. Okay, so that is the new definition of convergence of a sequence on the plane, or once you go with this abstract notation, so this one is gone. Once you go with abstract notation, you realize it doesn't really matter, the dimension doesn't matter. So I said it is a plane. Why is it a plane? Why it is not a space, three-dimensional space? If it is three-dimensional, why not four-dimensional or n-dimensional space? It doesn't make any difference whatsoever, as long as we understand what distance means precisely, and we will. At this point, we'll just be satisfied with this definition, which is, let me write it up again. So suppose AN is a sequence of points in, say, Rm. So AN converges to A in Rm if one, and the definition is just simply rewritten. Let me use the quantifiers this time. For every epsilon, there is an n such that n for any n larger than n, we have DAN A less than epsilon. Okay, so that's the definition, very compact. For any, there is for any, and the distance less than epsilon. So the idea, if you have given it thought in the past of the idea of convergence, is that of sequences especially, it is the epsilon is the distance. Well, if you see the picture on the left, then how do you illustrate it with the idea is that you have your A here, and then you create what would you put it, a disk around it of radius epsilon. Okay, and then what we're saying is that the sequence eventually ends up in that disk. Okay. So once again, it is at this point, what is the disk? Well, the disk is everything that satisfies this inequality will be considered a disk. So geometrically, if you want to describe it, or rather, if we try to visualize this idea, the definition, which is now is fully written, how do you visualize it? That's how you visualize it. You have no matter how small an epsilon you pick, no matter how small a disk around A you pick, the sequence eventually will end up within that disk. Okay, so instead of having an interval, which is what you have in dimension 1, in dimension 2 you have a disk. So eventually this sequence is inside of it. Then it's like a standard of accuracy that you improve and improve, and no matter what that standard is, it is met by the sequence. Okay, so this in other words, if you want to look at the contrapositive, that's another way. Well, I'm sorry, not the contrapositive, the negative. If you think about its negative, try to negate this statement. Wanna negate this statement? To understand the idea of convergence, let's take a minute and negate this.
There exists an epsilon for any n.
So in other words, there is a disk. What are the properties of that disk? Yes? For any n capital?
There exists little n greater than n.
Yeah. What happens to the inequality?
Flips.
What?
It flips.
It also flips, yeah. So there is such a disk around A that no matter how far we go with our sequence, it will not end up in the disk. It might visit it on and off, but it will not stay. The whole tail will not necessarily stay within that disk. Okay, so the idea is the same as in calculus, and we'll probably revisit this if we have time. But at this time, we'll just we're not going to be doing calculus. We're trying to do geometry. So, but this is how it will be applicable, but later on to calculus. So no matter what the space is, the definition is handy of convergence of either sequences or limits of functions or continuity of functions of any nature, of any dimension of the domain or codomain. Okay, so then we just the plan is to not to deal with this calculus problem, but rather understand this in the abstract, just like with algebra. And then there will be more applications. Once we understand it, just following that idea over here at the top, as you can this is what we would like to later on, just to illustrate the value of this approach of the abstraction, to see more spaces with different geometry, and yet so we can do well. Let's think about it. If we the idea of what geometry is. Okay, so let's start with examples. Examples of distances. So number one are dxy is x minus y, absolute value. Okay, number two are 2 dpq, and suppose these are they have coordinates, say xy, x prime, y prime. Okay, remember the distance formula for the plane? I'm sorry, I meant R2 here. What's the distance formula for the plane? Distance formula in terms of the coordinates. So I have 2 points P and Q on the plane. Their coordinates are respectively x and y, and the other one is x prime, y prime. Don't you remember this?
The square root of
Yeah.
x prime minus x squared plus y prime minus y squared.
That's right. Okay, so that is the distance formula on the plane, and okay, so you can certainly probably try to recognize that how you get one-dimensional case from two-dimensional case, but then once you do, you will start thinking about what about dimension 3. So then a similar picture to this, and so we are still talking about this. So this is dpq. The distance between those 2 points. This is how it's found. In dimension 3, we have points P is x, y, z, say. Q is equal to x prime, y prime, z prime. So the distance between P and Q is what? You don't remember the pattern? Let me see if I have an illustration maybe here somewhere. It might be helpful to remember the formula. Okay, maybe under linear algebra. I don't think so. I don't think so. But so instead of having a rectangle like this, instead of a rectangle, and with the 2 points at the opposite corners of that rectangle, we are talking about a box like this. And once again, the 2 points are in the opposite corners of that rectangle. I'm sorry, of that box. So maybe this P and this is Q. Okay, so then the distance that we're after is this. Okay, so any recollections yet? Well, yeah, here how it goes. You can find, say, if I call this point R, okay, so, well, first of all, why rectangles? The rectangle, I'm sorry, why this box, where does it come from? It comes from the axes, edges are parallel to the axis. Okay, so my axes will look like something like this. Maybe like this. Okay, so the vertical is z naturally, y to the right, and x towards us parallel to these edges, or the edges are parallel to the axis. So you realize that we can now figure out the sizes. That's where the starting point of this computation is. We can figure out the dimensions. Before we get to this, we can figure out the dimensions of the box. So what are the dimensions? Just as we did it with two-dimensional case, this is x prime minus x, absolute value, right, in that rectangle, and this is y prime minus y, absolute value. Okay, and then you can see how these two dimensions appeared in the formula. So starting with the rectangle in the two-dimensional case, the sides of the rectangle are parallel to the axes, and the dimensions of that rectangle are simply these absolute values, the differences between the two coordinates, just the way we did in the one-dimensional case, right? Look at it. Well, what is that at the bottom? Over here is x prime minus x absolute value. What is it? It's simply the distance between these 2 points, right? So we're using the dimension 1 distance formula in dimension 2, okay? And so that way we know these two distances on the x-axis, on the y-axis, and then these two numbers become the dimensions of my rectangle, and knowing the dimensions of my rectangle by the Pythagorean theorem, right? That's where the formula comes from. The Pythagorean theorem, so two sides, we know what they are, and by Pythagorean theorem we end up with the square root, right? Okay, so that's the idea of two-dimensional that we have to sort of extrapolate or use in order to determine the formula for dimension 3, and once again the idea starts with finding the dimensions of that box. Instead of rectangle, two-dimensional case, we have a box in the three-dimensional case. Okay. So dimensions of the box are what? What is this distance? What is this dimension? P is x prime y prime, z x y z, and q is x prime y prime z prime. So along the x-axis we measure the distance, and they all are engaged separately. Okay, so it will be simply x prime minus x, right? Absolute value, just as in the two-dimensional case or one-dimensional case, right? And then we do the same thing again and again. So it will be along the y-axis, it will be y prime minus y over here on the along the y-axis, and the vertical will be z prime minus z. So y minus y prime, and one more. This one, it will be here, z prime minus z absolute value. Okay, so these are the dimensions. X prime minus x, y prime minus y, and z prime minus z. Okay? And then we have to combine them in a manner similar to that formula, the distance formula at the top. Right? So you can guess if you like.
Because you're going
Yes, there will be an extra term in the inside of the square root. So dpq is x prime minus x squared. As you can see, the absolute value disappears once we square it. Okay, so that's the formula for you. You can derive it fairly easily because well, this distance in the xy plane. Okay, and you find it by the formula in for dimension 2, and then once you know what that is, you look at this triangle over here. Well, so let's not worry about it. Let's just take it for granted because we really cannot stop in dimension 2. We have to go to dimension n. Rn, x is equal to x1, xn. Well, let's say it's p. So what is an element of n-dimensional space? It is simply a string of n numbers. Okay, and once again, you can extrapolate. I mean, it is an n-dimensional space. Okay, so it means that there is no, we cannot visit that space. We cannot do measurements within that space. It is a man-made space. So there is really no choice for us to just to come up with an idea and then see if it makes any sense. Okay, how? Well, we see a pattern. We see a pattern. So 1, 2, and 3. We see what's happening. How you get more and more terms in the sum in that expression, and then so you have two terms, dimension 2 terms, dimension 3 terms, dimension n terms, right? The only it is entirely abstract, so we don't really have a choice but to just write up the formula and then see if it makes any sense. If it works the same way as well as in all other dimensions. Okay, so okay, so what's the formula? How about what's the formula? Well, try to extrapolate. So we remember we're doing abstraction, but it's interesting to notice that at this point we're not doing abstraction as much as we're trying to generalize things by analogy. So that's the kind of a stepping stone towards abstraction, is to try to generalize our understanding, our formulas from what we have been comfortable with into higher dimensions, higher or more general situations, on, and then just hope that they will behave similarly. That's what we did with algebra, and it did behave similarly. But why it worked out, because, well, it was tested, and so the axioms of group were certainly developed through trial and error, so that those axioms are the only ones that we necessary in order to have all algebraic things that we can dream of. Okay, so now we want to do roughly the same eventually with distances. At this point, we're not there yet. We just want to come up with a formula that for our n-dimensional space. So how do you extrapolate that idea of that formula over there? Well, I'm afraid I wrote the formula in such a way that it might be confusing. But the idea is this, once again. So look at the let me put it in a similar terms to that's a big deal, actually, making the notation such that so that it is similar and it is easy to generalize, and you see patterns. So okay, so the coordinates of P are x1 through xn, n numbers. The coordinates of Q are x1 prime through xn prime, also n numbers. So then the dimensions of that n-dimensional box, dimensions, unfortunately, same word for two different things, will be, once again, the differences, right? So these will be the dimensions. Okay? So we subtract them one by one, x, say, k prime minus xk squared. Then we add them all up. I want to use sigma notation just to keep it compact. And the final step is the square root. Works for any n that you can imagine. So do you see how we continue on with the pattern? Adding more and more terms, and we come up with this formula. We kind of did it mindlessly, but that's okay because we are not done. So we're going to confirm that this formula makes sense. So in what sense does it make sense? It makes sense that it will satisfy similar properties to some obvious properties of the distance that we have accepted for granted living in our physical space. They will be repeated in the high dimension spaces. So that's all you can ask for. Same as with algebra. Okay, so so the formula is there. What is that? What is the similarity? So then at this point we have to try to extract those properties, those which will end up being axioms of distances. So what is that distance? Distance could be that starting with low dimensions, obviously. Probably dimension 2 is complex enough. So this is dimension R2 is complex enough. And at the same, not too complex for everything interesting things to happen. Okay, so as you can see, so what is that? As you can see, it is a kind of a function. Well, to begin with, that is not an accident that we're using this notation. It is in fact a function. And then we're now we're trying to understand the properties of this function that we will then verify for high dimensional situation. Okay, so once again, it is a function of two variables, of p and q. As you can see, p is an element of point on the plane, q is a point on the plane, and so this is okay. Let's start with that before we get to the properties. We suddenly realize that our distance is a function. Okay, so that's the number one realization is the distance is a function. Okay, so if we realize it's a function, we have to explain what its domain and codomain are. So what is the domain? So once again a function. So suppose distance where? Okay, so suppose we have a set X starting with R2. Okay, so that's we take it R2 as an example where everything is, as I said, complex enough, but not too complex in order us to understand the potential pitfalls, and at the same time steer us towards the right answers. Okay, so the distance. So we're trying to come up with axioms, abstract axioms, for what it means to have a distance on a set X. So once again, we have set X as an example. X is R2. We realize the distance is a function. What is its domain? Once again, look at the formula. What's the domain? No. First of all, once again, we're talking about set X. So we're trying to do it in the abstract as much as possible. So we're talking about dpq. dpq is equal to something. the specific formula we're going to deal with later. Let's just look at this picture, this expression over here, and understand what it's telling us about distance d being a function. Okay, so how about before we talked about the domain, let's talk about the codomain. It is simpler. What's the codomain? The values. What are the values of distances? What is the nature of the distance, algebraically speaking? It's a number. The distance is a number, so it doesn't matter. We do it on the plane. Look at those formulas. Ultimately, you start with coordinates, but ultimately at the end of all this computation, you have a number. You have two locations. Distance between them is a number. That's all. So y is, so codomain, the answer is R. In fact, if you want to narrow down, you can put R plus here, because we know R plus meaning positive numbers or 0, so that we don't have to worry about negative distances. We don't want negative distances. Okay, so what is the domain? So once again, we have P belongs to X, and Q belongs to X. And Q belongs to X. Okay, so what does it tell you about the domain of such a function? I promise you know the answer.
It's X.
What?
Is it X?
No. P and Q. Any P and any Q can be combined together in order to produce one input of this function. So it's not X, but what?
P and Q.
No, P and Q are elements. Right, so P and Q, pair. It is a pair, as a matter of fact. Pair. A pair of elements of Q. Of X. A pair of elements of X, what do we call them? Where do they live? Pairs. Close. What do we call it?
Plane?
Is kind of a... I mean, X is not a plane anymore. X is just a set. Pairs of elements of X. What do we call them?
The subset?
No. No, not quite. Well, remember this notation, x cross y. So when you talk about, that's where the graph of a function lives. So if you have a function f from x to y, okay, then where does the graph live? And it lives in x cross y. Remember this? So you form pairs of x's and y's, and the set of all pairs form this Cartesian product. That's the word that we used. Okay, so we formed it specifically. The purpose was to create the place for the graphs of functions to live in. Okay, so that's the reason we created the x cross y, the Cartesian product of the space. But here's another application of that construction, and that is what is the domain of the distance function. It is the x cross x. So what does it mean? It means that you pick any elements in the first component, which is x, and another one pick in the second component, which is also x. So that's how PQ are formed. They live here. PQ, a pair, lives in x cross x. Okay, so like this. This is x, and this is also x. So any location here will be PQ. Well, what does it mean? It means that there is a P here, and there is Q there. Okay, which doesn't, I'm sorry, I'm out of time. Okay, so we'll just continue next time.